All right, so the second video for chapter 3, I'm going to now be looking at non-binary ionic compounds. So what happens now with non-binary is we're going to have a metal that's partnered with what's called that polyatomic ion. We have a list of polyatomic ions, right? And I've asked you to memorize that list. And this is in my courses. So you want to not only memorize the name, but the formula and the charge. Like all of that's important. So I recommend making flashcards, quizzing yourself somehow, but you need to remember that, like, for example, Cl(O4 negative 1 is called perchlorate. And the charge is going to be really important when we do equation writing, but also here with nomenclature. So make sure you start memorizing those. All right, so what we did in the first video when we were looking at binary ionic compounds, with regard to the metal, it's going to be the same for non-binary. So whether it's binary or non-binary, with the metal, you have to know, is it a type 1 or is it a type 2 cation? And it's going to be the same as what we did for binary. If it's type 1, we just name the metal. If it's a type 2 cation like iron, then we're going to need that Roman numeral again. Now, one little trick with memorizing the polyatomics is you'll notice that there's a lot of polyatomic ions that look very similar. Like you'll see sulfate and sulfite and phosphate and phosphite. And what I always recommend is memorize all your 8 polyatomic ions and then just realize that the ite is one less oxygen. That's all you're doing. So if you memorize that sulfate is SO4 negative 2, then sulfite is SO3 negative 2. If you remember that phosphate is P04 negative 3, then phosphite is P03 negative 3. All you've done is dropped an O. Okay, so some examples here. First one, we've got KHCO3. So just take out the first element, which is K, and we know K is potassium. And then when we look at our periodic table, we know that the charge of potassium, because it is a group 1 metal, is always a +1. So that's why we don't need the Roman numeral, because it's redundant. We know potassium's always a 1. Then the second part, right, is the HCO3. So the H is part of the polyatomic. So if I look on my list of polyatomics, HCO3, you have a choice. You can either write it as hydrogen carbonate or you can write it as bicarbonate. Up to you. All right, so potassium bicarbonate. The next one we have is FePO4. So Fe we know is iron. When I look at my periodic table, I know iron is going to require a Roman numeral. So I'm going to have to come back to that. And then I look at whatever that PO4 group is, that polyatomic. So on my list, PO4 is called phosphate, but what's also important is that I recognize it has a negative 3 charge. So when I look at this PO4 group, the polyatomic, right, it has 3 extra electrons. There's a phosphorus bonded to 4 oxygens, and there's 3 extra electrons there. It's got a negative 3 charge. There's one of those groups. So to balance, that one iron must be carrying a positive 3 charge. So my name here would be iron 3, and then we saw the phosphate, right? So the good thing about the polyatomic is you just name it as is. You don't change the ending. PO4 is called phosphate, so that's all we say. Next one here we have Mg, which we know is magnesium. On our periodic table, magnesium is a group 2 alkaline earth metal. So we don't need a charge, or we don't need a Roman numeral because we know the charge, right? It's +2. And then what I'm looking for on my list of polyatomics is H2PO4. All right, and if I look, and this makes sense, I know PO4 is phosphate. When I have 2 hydrogens in front, I say it's dihydrogen phosphate. So that polyatomic ion there, H2PO4, is dihydrogen for 2 hydrogens with phosphate. All right, magnesium dihydrogen phosphate. Now, if we go in the opposite direction, if I give you the name and we want the formula, the first one here is we have ammonium carbonate. And this is the only exception that we have for an ionic compound starting with a metal. Ammonium is not a metal, it's a polyatomic. All right, so I'm going to look, and we know because ammonium, there's no element ammonium. It's our only positive polyatomic ion we have to worry about. So when we see ammonium, we know that that means NH4+. Then carbonate from our list of polyatomics is CO3 negative 2. So just like we practiced with binary compounds, we need a balance of charges. So we can crisscross here. The only thing that's more complicated, just slightly, is that because it's a polyatomic, if we need more than one, we have to put it in parentheses. So ammonium has to go in parentheses, followed by the multiple of 2, so NH4, and then carbonate CO3. We only need one of those, so we don't need to put that in parentheses. The next one we have is calcium hypochlorite. Calcium we know is Ca, alkaline earth metal group 2, so +2 charge. Hypochlorite on our list of polyatomics is ClO with a -1 charge. So if I crisscross there, I would need 1 calcium, and then for the hypochlorite, I would need 2 to get a -2 charge to balance the calcium's +2. So I would write Ca parentheses, ClO parentheses, and then follow that with the subscript of 2. All right. The chromium 3 sulfate, chromium +3 charge, remember that Roman numeral gives you the charge on the metal, and then sulfate, notice different endings, right? Instead of "ide" like we saw in the last video, we're looking at eights and ites. So that's how we know this is a polyatomic. So when we see sulfate, we know it's not just sulfur, but SO something. And if we look at our list, sulfate is SO4 negative 2. So if we crisscross here, we'd need 2 chromiums to get a +6 charge, and then 3 sulfates to get a -6 charge. So Cr2 parentheses SO4 parentheses 3. All right. Now a hydrate, which we will look at in the lab, is an ionic compound that has water molecules inside the crystal structure of the salt, right? So Epsom salts is magnesium sulfate hepta for 7 hydrate. So hydrate just means water, and we name the number of waters in that molecule, in this case hepta for 7, using the same prefixes we do for covalent nomenclature, which we'll talk about in just a second. So if we see a hydrate, we use prefixes to say how many water molecules are there. And these are the same prefixes we use with covalent or molecular compounds. So when we have a nonmetal and a nonmetal, we, instead of looking at ions, because of course there are no ions, it's covalent, we use prefixes to just say how many of each element are in the compound. The prefixes mono, di, tri for 1, 2, 3, tetra, penta, hexa 4, 5, 6, hepta, octa, nona 7, 8, 9, deca, undeca, and dodeca for 10, 11, and 12. All right, so what we do here is we're going to have 2 nonmetals in the compound. For the first nonmetal, we name it as is, and we use a prefix, but only if there's more than one. For the second nonmetal, we always use a prefix, and just like we saw with binary ionic compounds, we always push that IDE ending. So an example here says, write the formula for a compound that contains 2 nitrogen atoms, so we'd say N with a subscript of 2, and 4 fluorine atoms, F4. Now if we were going to name that, the first nonmetal we name as is, use a prefix if there's more than one. So we want to say that there are 2 nitrogens here, so dinitrogen. And then for the second nonmetal, always use a prefix, so 4 would mean tetra, and then we push that IDE ending, so fluorine becomes fluoride. So N2F4 is dinitrogen tetrafluoride. Now the next one says, write the molecular formula for tetraphosphorus decasulfide. So tetraphosphorus means I have 4 phosphorus, so P4. Decasulfide, deca means 10, so sulfide means sulfur with a subscript of 10. So tetraphosphorus decasulfide would be P4S10. And then the other thing it has here is let's name S7O2. So 7 sulfurs would be hepta, sulfur, and 2 oxygens would be dioxide. So S7O2 is heptasulfur decaoxide. So covalent compounds, it's all about the prefixes, remembering the prefixes, making sure the second element gets an IDE ending, and pretty much always use a prefix except, let's say, just as an easy example, because we all know this one, CO2. If you only have one of the first element, then you don't use a prefix. So for CO2, instead of saying monocarbon dioxide, we just say carbon dioxide. All right. Now the second element, remember though, always need a prefix. So if I have CO, then I have to say carbon monoxide. All right, now the next section talks about acids. All right, for acids, we're going to have sort of the same issue. We're going to have to look at, like we did with metals, is it a binary or non-binary? And that's going to change the way we name it quite a bit. All right, so if it is a binary acid, first, acids are ionic in nature, so you still have a cation and you still have an anion, which means we're still going to have charges to balance. The special part about acids, though, is that the cation is always H+. The anion can either be a simple nonmetal or it can be a polyatomic. If hydrogen is partnered with just a nonmetal, that means that this is a binary acid. And binary acids always have a very special name. They are hydroic acid, where all we have to do is plug in the stem for the nonmetal. So names like hydrochloric acid, hydrobromic acid. If a hydrogen is partnered with a polyatomic, now this is non-binary. It's going to be more than 2. And now what we want to make sure and remember is do not use hydro when it is a non-binary acid. And instead what we do here is if the polyatomic ion ends in 8, we change 8 to ic and add the word acid. If the polyatomic ion ends in ite, we change ite to us and add the word acid. All right, so that's how we handle acid nomenclature. All right, so on the next page, we're going to do a couple of examples with acids, and then we're going to just sort of look at a bunch of different compounds and kind of push everything together. All right, so first acid we have here is Hi, and I know it's an acid because it starts with H. That's my cue. Whenever a compound starts with H, I know it's an acid. So if your first element is H, we know it's an acid. The other thing I look at now is it's only 2 elements, so I know it is a binary acid. And binary acids, like we said, have a very special naming system. So we would say hydro, IOD for iodine, ic, and then acid. So Hi is hydroiodic acid. Now HiO3, the next example, it still has hydrogen in front, so I still know it's an acid. But now there's more than 2, so this is a non-binary acid. And so instead, what we want to focus on here is what is the name of the polyatomic ion? So when I look at my list of polyatomic ions, IO3 is a polyatomic ion that's called iodate. So what my rule is that if my polyatomic ion ends in 8, I'm going to change 8 to ic. So I'm going to cross out the 8, and I'm going to replace it with ic. IC, and then add the word acid. So HiO3 is iodic acid. So the next one I gave you, just to kind of, again, emphasize hydro, is which of these 2 acids would be bromic acid, HBr or HBrO3? And what's important is because there's no hydro in the name, I know it's not binary. And so it has to be the HBrO3. All right. Couple more here. We have H3PO3. Again, we know it's an acid because it starts with H. It's non-binary because there's more than 2. So I need to look at my list of polyatomic ions. PO3 is called phosphite. So what we saw earlier is with the iodate, 8 goes to ic, but with ite goes to us. Now instead of phosphus, we're going to say phosphate. phosphorus acid. So sulfur and phosphorus are the only two that kind of bring back that extra syllable. So instead of it just being phosphorus, it's phosphorus acid. Now for the next one, we have Hpo3 negative 2. What's different here is, yes, there is an H in front, but it's technically not an acid because it's carrying a charge. And what we said was, if it is a group of atoms that carry a charge, it's a polyatomic. So Hpo3 negative 2 is not an acid, it's a polyatomic ion, and we name that like a polyatomic ion. It would be called hydrogen phosphite. All right, so just a little bit of a distinction. Now the polyatomic ion, when we name it, it's going to be part of a compound, not by itself. But that's why we don't name H3PO3 like trihydrogen phosphite. It's an acid, so we follow the acid naming system. It'd be phosphorus acid. All right, going in the opposite direction, what is nitric acid? All right, acid means the compound starts with H+. We are missing hydro. There's no hydro here, so that tells us we know it's a polyatomic ion. We know that the ic came from 8, so we are looking for nitrate. When I look at my list of polyatomics, nitrate is NO3 negative 1. And since hydrogen is +1, I just need one hydrogen and one nitrate. So nitric acid would be HNO3. All right, now P2O5, we're changing gears a lot, right? Very substantially, because now what we're doing is we're starting with phosphorus, which is a nonmetal. And that means that this is a covalent or molecular compound. And what we saw was when you have a covalent compound, we use prefixes. So P2O5 would be diphosphorus, and pentaoxide or pentoxide. P2O5, diphosphorus pentaoxide. All right, Fe2O3. We know iron is a metal, but it is a type 2 metal, which means we're going to need a Roman numeral. So we're going to say iron for now, put parentheses, we'll come back for the Roman numeral. And then what we have to look at is, because this is a binary compound, it's going to end in IDE, so oxygen becomes oxide. Now for the charges, I have to start with oxygen. Oxygen is a -2 charge. That is the subscript on the iron, so then the opposite will be true. The subscript on oxygen, which is a 3, is the charge on the iron. So this is iron 3 oxide or ferric oxide. All right, next one, Cri3. Okay, so again, chromium is a metal. It's a type 2 metal. It's a transition metal. So we're going to have to say that this is chromium and then put a parentheses and come back later for the charge. And then it's binary, so iodine becomes iodide. All right, now for the charge, since iodine is -1 and there are 3 of them present, that means the chromium here must be a +3 to balance. So chromium 3 iodide. All right, there's 3 examples that go together in the next section. I've got PbNO3,4, PbNO2,4, and Pb3N4. All right, and here's what makes these different. It's going to be the last 3 letters. Now all of these contain Pb, which is lead. It's a type 2 cation, so we're going to need a Roman numeral for each of these. But what changes is in the PbNO3,4, NO3 is a polyatomic called nitrate. And nitrate carries a -1 charge each. Since there are 4 in the compound, the lead must be a +4. And again, you could see that crisscross is working for you here. All right, that charge of 4 is coming from the subscript on the nitrate. The same is going to be true in the next example, PbNO2,4. The lead is a +4 charge, but now instead of nitrate, we have nitrite. 1 less oxygen gets the ite ending. Then the very last one, it's just Pb3N4. Nitrogen is a -3 charge, so that means the lead must be a +4 charge. And what's different here is that because this is a binary compound, the ending will be nitride. IDE. All right, couple more here, CS2. All right, CS2, we are starting with a nonmetal. So again, that's where we use our prefixes. So CS2 would be carbon disulfide. All right, so again, binary, IDE ending, but prefixes di because it's covalent. Na2S, now I have a ionic compound. Sodium is a type 1 metal, and this is binary, so we're just going to say sodium and then sulfide. IDE because it's a binary compound, just Na2S. Last one here, Na2SO3. Again, sodium, but now what's different is it's partnered with sulfite. Polyatomic SO3 is called sulfite. So sodium sulfide and sodium sulfite, just to show you there's just one letter difference between those two, but a completely different compound. So that takes us through nomenclature, and there are other videos posted to help practice some more because it's a lot of information.